This diagram illustrates the core-level scan pattern generation process used in ATPG tools like Tessent. It begins with three key inputs: the scanned inserted design, a do file, and a test procedure file. These inputs feed into the pattern generation engine, which performs a series of automated steps to produce test patterns optimized for retargeting. The process includes enabling retargetable pattern generation, configuring the core for internal mode, generating all required pattern types, and addressing any test coverage issues. After these steps, the tool writes out several deliverables: retargetable patterns, PATDB, fault lists, flat models for diagnosis, core description files, and verifies the patterns using Verilog simulation. Finally, the output consists of four main deliverables: core patterns, core fault list, core description file, and a flat model for diagnosis. These are essential for subsequent chip-level retargeting and diagnostic analysis, ensuring efficient and accurate testing across multiple cores. This diagram illustrates the core-level pattern retargeting process used in scan-based DFT. It begins with inputs such as the top-level design, do file, test procedure file, core description files, and core patterns. These inputs feed into a structured workflow that enables efficient test pattern generation by leveraging existing core-level patterns. The process starts by enabling pattern retargeting and loading the top-level netlist, where cores can be gray-boxed or black-boxed for abstraction. Next, core access and internal mode are configured, followed by inputting core-level description files to identify individual core instances. Design rule checks, DRCS, are then run to extract scan connectivity between cores and the top-level logic, ensuring valid core embedding. Afterward, core-level patterns from each core are imported, merged, and retargeted to the top level. The final steps generate retargeted patterns and a top-level core description file, which supports failure analysis and future retargeting without reusing the netlist. The deliverables include both the retargeted patterns and the updated core description. This diagram illustrates the flow for generating test patterns in external mode during scan-based DFT. The process begins with inputs such as a scan-inserted design, do file, test procedure file, and core fault lists. These are used to configure the chip's cores into external mode, enabling testing of interconnect and glue logic. The tool first inputs the top-level netlist, optionally gray boxing cores to reduce complexity. It then configures each core to operate in external mode and runs design rule checks DRCs to ensure compliance. Core-level fault lists from internal mode pattern sets are imported to guide the generation of new patterns focused on interconnect and glue logic. Patterns are created specifically for testing the connections between cores and any additional logic required for integration. These patterns are written out and full chip test coverage is reported, providing visibility into the effectiveness of the test set. The final deliverables include interconnect patterns and a full chip coverage report. This diagram illustrates the process of merging scan patterns generated for different modes of a core at the top level. On the left, Mode 1 patterns are generated targeting sub-block 1, while on the right, Mode 2 patterns are generated for sub-block 2. Both pattern sets are created independently at the top-level design. Each pattern set includes core patterns and a corresponding core description file, which contains test configuration details such as clock settings and scan chain information. These files are essential for defining how the patterns will be applied during testing. The final step combines both pattern sets into a unified set at the top level, resulting in a merged configuration that supports testing both subblocks under their respective modes. This approach enables efficient test pattern generation without requiring full netlist integration, leveraging mode-specific constraints to optimize memory usage and test coverage. This diagram illustrates the process of merging scan test patterns generated at different levels in a hierarchical design. On the left, Mode 1 patterns are generated at the top level for sub-block 1. In the center, Core B patterns are generated independently at the core level using its own test configuration. The core-level patterns are then retargeted to the top-level context by incorporating the core's description and pattern data into the top-level environment. This allows the core's internal logic to be tested while maintaining compatibility with the overall system mode. On the right, the merged result shows both sub-block 1 and Core B integrated into a single top-level test structure. The retargeted Core B patterns are now aligned with the top-level Mode 1, enabling efficient and comprehensive testing without read-enable generating all patterns from scratch. This diagram illustrates a multi-core design used in scan pattern retargeting. It contains two identical CPU cores, labeled CPU-1 and CPU-I2, and one NB core, labeled NBI. These cores are connected at the chip level, allowing test patterns to be generated at the core level and then retargeted for efficient testing. The CPU cores are structurally identical, enabling the reuse of test patterns across both instances. This is key to retargeting. Once a pattern is created for one CPU core, it can be applied to the other without modification, reducing test generation effort. The NB core is distinct from the CPU cores and requires its own pattern set. However, at the chip level, all patterns are synchronized and broadcast appropriately to each core. This example demonstrates how retargeting improves efficiency by leveraging core similarity while maintaining individual core-specific test requirements. This diagram illustrates a hierarchical scan pattern retargeting flow in a multi-level design. At the top, the child core contains internal scan chains that generate test patterns. These patterns are then passed to the parent core, which acts as an intermediate wrapper level. The parent core receives and processes the child patterns before forwarding them to the chip-top level. This flow enables incremental extraction and retargeting of scan patterns across multiple design levels, ensuring efficient test generation. The process is recursive. Each core can contain multiple child cores, and the chip can include several parent cores. The final retargeting occurs at the chip level, where all core-level patterns are unified into a single test set for the entire chip. The core and core scan pattern retargeting process starts at the lowest level of the design hierarchy and proceeds upward, one level at a time. First, internal mode patterns are generated for all child cores within a parent core. This ensures that each subcore has its test patterns ready before moving up. Next, core extraction is performed only to the parent level, preserving the integrity of lower-level structures. The process then checks whether the next higher level is the chip level. If not, the wrapped core from the next level is loaded into the current context. If the